very closely related topic to Effie, talking about these cold atoms coupled to photonic crystal waveguides. It's kind of, I guess, an interesting story that it seems like every time I'm working on something, I see a paper appear on the archive which Effie has written, and I'm like, oh, okay, so he's done the same work exactly. So you'll see that there's some closely related topics, but I guess we, to some extent, look at things from a different view. So I'm from the Institute of Photonics in Barcelona, and I'm in Derek Chang's theoretical quantum nanophotonics group. So it's kind of getting to the point now where just about all the members of Derek's group are now working on this kind of atoms coupled to nanophotonics. I think he started out with people working various things, and this kind of nebulous photonic stuff is kind of drawing everyone in, so everyone's getting excited about that and working on it. In particular for this work, Hissam was a part of this work, as well as Tommaso, and Tommaso is here, so you can ask him questions about this stuff as well. And also Anna is here, and she's working on what was just being discussed before, which is kind of this motional degrees of freedom for these atoms near photonic crystals. So I guess, and also to mention our collaborators, we've worked with Alexei, and obviously Jeff Kimball's group is kind of the key motivation for this. He's really been driving kind of where our ideas are coming from and what we want to look at. So, I mean, we don't really need to motivate this anymore, but I guess kind of the old system used to be, you know, if you want to couple an atom to a photon, which is a good thing to do for quantum information and just generally studying photons and atoms in general, you put it in the cavity, and this can be like two big glass mirrors on a microscopic scale, but what you find then is that this scales with the inverse volume of the cavity, so the smaller the cavity, actually the better the coupling is. And so now we've seen that this morning that there's now this kind of change in how things are done. Instead of having these macroscopic cavities, you're now switching to this kind of nanophotonic systems where you're really confining the light down to a scale where it couples very well to an atom. And this is great. So we've seen that, you know, you can kind of do cavity QED on an unprecedented scale, like in Jeff Thompson's talk this morning. And that's really nice, but I guess the question that we're kind of asking ourselves, and I guess Jeff was talking about this morning as well, is that is there something more to this kind of nanophotonics coupled to atoms, which is not just your normal regular cavity QED, which we kind of fairly well understand from the sort of James Cummings kind of style theory. So I guess I'll try to convince you that the answer is yes, and maybe you don't need to be convinced after Jeff's nice talk anyway. But so really, in the Kimball group experiment, they have this nice photonic crystal waveguide, and then they hope to really trap a lot of atoms. They've got a few at the moment, but then if they can trap a lot of atoms, then this really opens up a new regime of kind of experiments where you can look at kind of the many body physics in this kind of regime where that every atom is strongly coupled to this waveguide, and then also, as Effie was just showing you, you can get these kind of long-range interactions between the atoms as well. And also, I'll later talk about photon interactions as well. So just to go back and kind of reiterate what this photonic crystal business is, of course, you begin with just a normal waveguide where if you put some light in, it kind of gets internally reflected and then pops out the other end, and that's nice. But then if you put some holes into this, then you can enter a new regime where you can kind of control the dispersion relationship for the light. So now, at this point, if some light is entering the system, and it's on the right wavelength scale, so that the period of these holes is matching, is like the right scale to the wavelength, then you can get constructive interference, which means that all of the light gets reflected back. And in this regime, the light is kind of struggling to get in, and it kind of forms this evanescent field going into the crystal, but it never manages to propagate out the other end. And instead it kind of gets reflected. And this was the basis for this kind of nearly perfect mirror. And then, of course, the kind of representation of this and the kind of dispersion relationship for this system is that at some frequency you get a gap in the bands of this system. So in this band gap, this is just representing that at this particular frequency, then light cannot propagate through the system. And so, as we saw this morning from Jeff Thompson, this kind of system can be used to make this nice photonic crystal cavity. You just take two of these mirrors, put them on either side of the atom, and then you've got this kind of nice cavity cutie system, which is by far better than any optical cavity that was being fabricated before. So that's really nice, but then we want to look at this from a sort of different perspective and see, you know, what can we do which is not this cavity cutie stuff. So instead of taking this photonic crystal with the defect, where there's some holes missing, we just look at this uniform photonic crystal waveguide. And then you can kind of think, wow, what if I trap an atom near this, like Jeff Kimball was trying to do? Then I can think of exciting this. So imagine I drive it from a laser externally from the side or something. And then if it's excited, and so what I want to do is I want to drive the system inside this band gap where there's no propagating modes of this fiber. And in that case, when I drive this atom in this regime, so I'm driving above this lower band edge, then the atom can no longer emit a photon into this waveguide. But as we kind of saw before, there's still this evanescent kind of tail at that frequency. So what can happen is that the atom sort of couples to a localized photonic cloud which is around the atom. And so this forms this atom-photon bound state. And I guess the really nice thing about this, which Effie was just describing, is that now you can use this to kind of mediate interactions between atoms. So you have your one excited atom here, and it kind of couples to this photon cloud around it. And then you have another atom here, which is distance r away. And they can see that cloud, and it can potentially absorb the photon from that cloud, and then can swap the excitation kind of back and forth between the atoms. And this leads to this, if you kind of eliminate the photonic part of the system, then this leads to this effective spin-spin interaction where you're exchanging excitation between these two atoms. And in the kind of the most straightforward case that you can imagine, this is just a kind of exponentially decaying interaction. So this the interaction kind of coefficient depends on R, and it depends in an exponentially decaying way. And well, another thing that's really nice about this is that it's quite tunable. So we kind of, as you get closer to this band, then you kind of expect that you're coupling stronger and stronger to the band. And as the band is kind of propagating, that kind of extends this cloud out. Whoops. Oh man. So you get, as you go closer to the band, by tuning whatever your driving frequency of the atom is, then you can change the size of this photonic cloud, and then that in turn changes the size of your interaction. And I guess just to kind of look at one way of interpreting how this system can really be seen is that this photonic cloud coupled to this atom can actually be shown to be exactly analogous to a cavity mode. So it's as if this this atom was coupled to a cavity of this length. So it's like around where the atom position is, you're sticking two mirrors, and then this kind of atom photon bound state is just then analogous to the dress state of this atom with the cavity mode. And from that you can find kind of like the cavity QED parameters, like the tuning of the mode from the atom, and also like the coupling between this cavity mode and the atom. And this is just kind of what you'd expect from the length of this cavity. So then, now that we know this sort of the same as a cavity, you can kind of apply this cavity QED logic, and once again you get this kind of this interaction, which is just like you would expect in a cavity QED system. So if you had two atoms that were farther tuned from the cavity, then they would have this dispersive interaction. The difference here is that this length dependence, you have this length dependence which has this exponentially decaying envelope around where the atom is. And so this changes it from sort of being this infinite range interaction which you have in a cavity where if you put two mirrors somewhere and you're bouncing light back and forth, then the atoms will interact more or less the same at any point depending on the mode function. But in this case, this kind of decays exponentially and it starts to look like sort of a finite range interaction. And at the same time, since we've identified these cavity parameters, you can now kind of understand how loss will work in this system as well, because in cavity QED, there's this parameter called the cooperativity, which describes really well sort of how things work. And this is really just the ratio of this, the good stuff, which is the coupling between the atom and the cavity, to all these kind of extra bad stuff. Well, this one may not necessarily bad, but the decay rates of this mode. So this is the spontaneous emission rate, and this is kind of the cavity decay rate. And so this allows you to kind of parameterize how well you expect these photonic crystal systems to work if you have some idea of what gamma and kappa is, and then you can find your cavity coupling for your particular length of cavity that you designed by tuning the tuning, and that will give you kind of an estimate of this cooperativity. So just to kind of summarize some results that we have in our paper without actually really going into the details. So I'll just give you this reference, and then you can, if you really want to think about these things, then you can go and look at this. So one of the things that you can do is instead of just having these kind of spin-spin excitation exchange, doing some playing a little bit with the kind of level structure of the atoms which are sitting near the photonic crystal, and adding some classical fields, then you can create other kind of spin-spin interactions. And so to some extent, we haven't really explored this full space of what all full range of spin interactions you can achieve, but for example, this is kind of like an icing type interaction. And that's very nice, and you can also alter this kind of exponential decaying interaction as well. So the base thing that you always have is this exponential decay, and you might say, well, if you're a condensed matter physicist, you would say that's a short-range interaction. And that's true, of course, if you go to the thermodynamic limit where you have infinitely many atoms, then that's a short-range interaction. But actually in a physical system, you're always going to be bounded by some size. And as Effie was saying, you can, in these systems, you can really shift this length range so that it can be actually much greater than the system size. And in fact, you can conceive of a system where you can have uniform interactions over the whole system. Or another example that we've derived is that you can have, just by having a couple of different driving fields, then you can kind of add together two exponentials to gain some sort of other kind of like algebraic decay of of the polynomial decay of the interaction. And also, one of the potentially more interesting things about this thing is like you look at this Hamiltonian initially perhaps and you think, oh, it's just a spin-spin interaction. I have these spins and then I'm going to do some quantum simulation of some spin Hamiltonian, but also these atoms are free to move. So what you actually have is this really quite rich system where not only do you have these spin-spin interactions, but you have spin-dependent forces where just flipping the spin of one atom or the other atom can change the force on the rest of the atoms in the system. And so this, coupled with the fact that you couple very strongly photons from the outside into these kind of atom systems, this gives you this new kind of system where you've got these strong long-range spin-spin interactions, you've got photon degrees of freedom, and then you've also got this nice photon coupling in and out from the system. So I guess that's all summarized in this paper. Now, sort of to take another kind of step in the system to see what else we can potentially see, we looked at this photon-photon interactions in the system. So just as Effie was saying, and also Thomas Paul was saying earlier, it's kind of if you have strong enough interactions between your atoms, then you can use them to mediate interactions between photons in these kind of EIT systems. The reason why this system is potentially interesting, we think, is that the range for tuning these interactions seems to be kind of, we have a bigger space to work with than Rydberg atoms potentially. I think with Rydberg, more or less you're stuck with this 1 over r to the 6 potential. Maybe there's ways to get around that, but this kind of leads to a situation where if you want to have long-range interactions which are big enough to be felt over some size in your system, then you're actually really detuning like these EIT resonances. So you're really doing this thing where you're switching from, as Thomas was saying, from a 3-level EIT system, and you're just blasting that off resonance to be a 2-level system. So we kind of look at this system as maybe a potential way to do something a little bit different, where you can sort of stay in this 3-level system and sort of tune around that with these long-range interactions. And sorry, I should mention that this is with Tommaso. So once again, questions about this can be asked to Tommaso as well. So you might be wondering now, I've kind of been talking about these long-range interactions which are mediated by this band gap system, and how would I actually couple photons in if I'm in the band gap? So what I really want is a system where I can send photons through an atomic medium, and the photons kind of go in like a waveguide, but then I also have this band gap interaction. Unfortunately, this is possible in the Kimball group experiment, because they have this nice system where you have these two different beams for the photonic crystal, and each one has individual modes of its own. And then when you bring them close together, these two beams, the modes start to hybridize with each other, and you can get like different symmetries, and that basically means you can have one mode that can act like a waveguide for the atom. So if this is the atomic frequency, then I can have one mode that can act like a waveguide, and one that can do I can do my band gap interaction. So I can have my atoms sitting there, and they can be interacting via this band gap thing, but then also I can send my photons down here, and they can be sort of propagating in a nice waveguide. And that's Jeff was showing stuff earlier this morning about his showing the TE mode versus the TM mode, where the TM mode was the sort of waveguide mode, and this was the kind of band gap mode. So just to look at kind of, I don't know, a toy system of what this photon-photon interaction is about. So imagine that we can make this kind of dispersive interaction between two excited state atoms. So I'm just going to have like a bunch of two-level atoms sitting next to a waveguide. And then if I have this dispersive interaction where one atom, the excited, shifts the energy of the other ones, then if I put a photon in on the resonance with this transition, then potentially it can excite one atom, and then that shifts the energies of all these other atoms. And then for another photon in the system, then it's going to see a different kind of susceptibility. So obviously this level is shifted, and now it only has this frequency, and so its susceptibility gets shifted across. And so this leads to a kind of long-range change in the refractive index due to one photon being somewhere else for some photon being in another position. Of course, we don't really want to do that because two-level atoms are bad in that you're going to have strong absorption near this resonance where this effect is happening. So you want to switch to this EIT system where you add an extra level to your two levels, and then you have this kind of this transparency in the middle of your susceptibility, which allows you to propagate photons through the system without loss, and then you also have this nice slowing of the group velocity. So I think I don't have to explain this now because Effie already explained it, how you kind of engineer this sort of style of interaction where you take your dipole-dipole interactions, which I showed the band edge, and then you kind of just drive them off resonantly, and then you can get a kind of interaction between these S states, the third level in our EIT system, to create this kind of dispersive interaction. And just to kind of consider a nice model which gives us an intuition, we can consider this this case of infinite length interactions, which can be created in the system by just really extending the range of this interaction so that it's greater than whatever my atomic ensemble length is. And in that case, so I put my three-level systems near my waveguide, and then if I have one photon in here, it's going to propagate through the system on EIT resonance at this two-level EG transition frequency. And that EIT will work perfectly well for that single photon. But then, of course, whenever it's traveling through the system, it's creating this spin wave component, which is putting some component in S, and that's shifting the energy of these other atoms up. And so that makes it difficult for another photon at this frequency to come into the system, because it's going to be off resonant with EIT and it's going to be lossy. And instead, this second photon is much better going in if it comes in with this frequency, where you add that kind of this interaction shift. And then you can kind of see that this photon is also going to shift the energy level of this one. So if you want a fully consistent system for two photons going through the system, then they're both going to have to be going at this frequency, psi G plus U. So this gives us this kind of idea of number correlated transmission. So if I just put some sort of coherent state into the system to begin with, and depending on what frequency I drive at, then I can kind of expect that the output is going to be more dominated by a single photon or two photons, or going down the ladder you can add extra U's, and then you'll get whatever you want at the end. So the question is, does this really work? And to study that, we use this spin model, which Derek has developed and has been sort of worked on in our group a lot. And really the basis of this is that if you have atoms coupled to a one-dimensional waveguide, then each atom couples kind of with this gamma 1D, which Jeff was talking about this morning, which is kind of this coupling into here. So, and then if I excite one atom, it has kind of two options. The photon can go out here, or the photon can go down here, and then it can kind of couple to this, or it can also escape. And this kind of dynamics can actually just be fully captured in this waveguide effect of Hamiltonian, which is exchange of excitations between the atoms, and it also describes it's non-Hermitian, so it also describes this kind of decay of the photons from the atoms out, which can be collected as well. And so this kind of switches you from describing now these complicated photon modes, which depend on continuous degrees of freedom, to this kind of this nice discrete system where I'm just taking care of what the atoms are doing. And as we saw yesterday from Shanli, this system is kind of like an input-output, like cavity QED input-output. So you have this kind of black box, which is the spin model of this atom. These atoms all coupled to the waveguide, and their actual own atomic like degrees of freedom. They're the level structure inside the atoms, which can be arbitrary in the system. You can just add this into the system, and really all that matters is from the photon side of things is the field that you're putting in, and then you can calculate what this field is out from these dynamics and the input photons. So, and this is kind of the equation for the output field. I mean, it really just depends on this input modes and the kind of the atomic coherences which you find after evolving this system. And so that's nice, as I said, that you can reduce this dynamics to just studying these n spins, but it's also nice in that really you can add lots of different things to this thing. You can add your spontaneous emission loss, or you can add these 3-level EIT atoms or multi-level atoms, whatever you want to do. Recently we've also done the system with vacuum-induced transparency, where you can add like a cavity mode in there as well. So this is all very good, and it's basically it reproduces numerically to very high precision the kind of dynamics you'd expect from EIT. So you can match it with kind of exact results, and it agrees exactly. So what you then get from this system, so as I was saying, I'm looking at this number of correlated states. Then now if you look at just continuously driving this system, then so this is the single photon transmittance, and this is dependent on the tuning parameter here, which is the 2-photon tuning here. So I'm tuning this, not this one, but tuning the input laser and seeing what I get out the other side. And then obviously for EIT on resonance, then for the single photon part, this interaction strength, the change in interaction strength does not change the transmittance at all, but for the 2-photon part, so if I change the interaction strength, then I actually see that the point where I'm resonantly going through the system, getting my 2 photons out the other side is dependent in this kind of linear way on what my interaction is. So I can also kind of generalize this a little bit and consider it rather than just a infinite range interaction, like a step potential. And in this case, so if my atom is excited here, then it's kind of interacting with all the atoms in this kind of boundary, and then not with these ones. And then you can look at the spin dynamics and see the same. See what you kind of expect is that, if for driving at the single photon frequency, then there's this region in the middle where I'm really not getting any spin population in the two kind of photon manifold, because so this is kind of the population, the J spin and the L spin, and yeah, so I don't get anything within this region here because there's this interaction, and so two photons don't want to sit beside each other, but they can sit out in this region when they're well separated. And then alternatively, I can look inside this box, and actually I can see these like interesting. You can see the modes of like a square well potential. So, for example, this is the third mode of this box, and it propagates through the system like this. Whereas if this kind of interaction potential wasn't there, it would sort of disperse out. So we now kind of generalize this even further, and we look at this system where we really try to tune these interactions using these band edges. So one thing that you can think about is, while I have this normal interaction from driving inside the band near the lower band, but what if I add like the other band on the other side? Make this close enough that this interaction is the sum of these two bands. And then in this case, the result is that I get this kind of like molecular looking interaction. And then I can think, well, maybe I could have a bound state in this kind of dip in the potential. And I guess to do that, then I would like also that my two photons, which are separated now by this length r, whatever this minimum is. So these are well separated photon pulses. Then I would also like them to have an effective mass, which I can design as if it was saying with the dispersion relationship in EIT. And then in the system, then what I expect is that I have two things with an effective mass, and they're separated they're in this kind of harmonic-like potential, and then I can maybe think about whether I can get sort of phononic oscillations of this system. And so this is, hopefully this will work, a video, but we'll see. So this is kind of looking at the two photon wave function, where this is the relative coordinate. So this is the separation, and this is kind of the center of mass. They're always moving through the system. And this is kind of what I would expect from the oscillation of my spring, my two particles connected by a spring, if I kind of separate them a little bit. So I stretch the spring to begin with, and then see what happens. And then, lo and behold, it follows it. So I get this kind of two photon wave packet, which is oscillating around this potential. So this is just another view of that system. I get this kind of oscillation, and at these different points you can kind of see like the two photons are pushed together a bit, and then at the other extreme of the oscillation they separate out again, and then they kind of come back together again at this position 3 after an oscillation period. So that's kind of an example of sort of, I guess we were trying to think of like what's the kind of coolest thing you can do with these tunable interactions. So we kind of see this as, I mean, it's nice that you can make these photonic molecules, but it really is kind of, for us, a kind of stepping stone towards going towards like a developing how this system of photons with interactions works, and like extending that from just one photon to two photon, then going to higher body systems, and then you can imagine going to this kind of many body pulse limit where you're, thinking about crystallization in a sample or something. So that's very nice. And in general, I hope that I've kind of shown you that this new kind of system that Jeff Campbell's group is building is very nice. That it has these new kind of this new potential to build this system where you have this strong photon coupling with phonons and with spin coupling. And I guess these are sort of examples of what you might do with that, but really the next step is, you know, is this huge kind of area of what else is out there, which is left to be discovered. So, thank you.
Questions? Yeah, so indeed, I agree that these photonic crystal structures have many great properties, as was pointed out a few times today. But also in these structures, I guess atoms which are close to the non-photonic structure will suffer from some ground state decoherence. And now I want to ask, in what way is the ground state decoherence that you assume for your lambda system influencing the effect that we get?
So do you mean which ground state? Do you mean like the S state or the G state?
Well, you have a lambda system, right?
Yes.
Ground states, and there will be a dephasing or decoherence between these two states.
Yeah. So I guess one of the things we have studied is really the effect of this interaction potential on this state, because when you're adding this this potential, you're driving this S state up into this extra state, which I haven't shown here, but then that's coupling through this photonic crystal waveguides, doing this dipole-dipole exchange, and through that you get an extra loss to this kind of S term, and that's really determined by what I was saying earlier, the cooperativity of this cavity, this effective cavity mode that you've built in the photonic crystal. So if you can make that small enough, then that obviously improves the coherence of that state.
You have this rather cool two-photon wave function. Can you give a number on the time scale here, or is it what time scale would this be?
You mean how
this movie?
How long I need to? Yeah. So.
Or is it just an abstract time scale?
This certainly doesn't have a time scale on it. Yeah. Yeah. I mean, so really, so the things I have involved here is the optical depth of my entire system and the group velocity of this thing, and really the issue here is you need a large optical depth, really. I mean, the time scale is kind of doesn't really matter. You can adjust the group velocity to be what would you want it to be, but really you have to be able to fit these two pulses inside your kind of atomic ensemble. And then if you want to see this kind of nice dynamics where they're separated, then they have to be separated, and then they have to have a little bit of time to get through that. So you're kind of limited by how well you can fit a pulse inside the system, and that's determined by this kind of pulse bandwidth delay product. So.
All right. Further questions? Okay, then we conclude today's program.